Hello, and welcome to a lecture on Stage-Cascade Analysis. I'm Steve Ellingson. Here's an overview of this lecture. Gain, sensitivity, and linearity are the three primary considerations for receivers. We now consider how to calculate the relevant parameters given a cascade of two ports. In other words, when we design a receiver, and we can describe that receiver in terms of a cascade of two ports, how can we take the individual parameters of those two ports and consider them together and come up with an overall assessment of gain, sensitivity, and linearity? So first we'll talk about linearity, specifically in terms of second order intercept and third order intercept, and we'll do that for cascades of two ports, and I'll show you an example. We'll talk about the noise of cascades of two ports, and there we'll be using the parameters of equivalent noise temperature and equivalently noise figure. And then we'll get to stage cascade analysis of both of these types of parameters jointly, and we'll talk about the significance of stage order. And I'll show you an example. So first, the input third order intercept point of a cascade of two ports. So here I have two ports. Here's the first one. Here's the second one. The input to the first two port, I'll give the name x of t. The output of the first two port is y of t, and we'll use the subscript 1 to indicate it's the output of that first two port. And the output of the second two port, we'll give the name y of t with a superscript 2 to indicate it's the output of the second two port. And then the two port we'll describe in terms of the memoryless polynomial response model with coefficients as indicated here, and similarly for the second stage. So we can immediately write, in terms of this memoryless polynomial response model, the output of the first two port, and it's simply this. It's a function of x, the input, and then here are those coefficients in the model. And note that we're ignoring a naught, as we've discussed in previous lecture. We're usually free to do that in RF analysis, but make sure you understand the reasons why we do that. And then the output of the second two port can be written as shown here. Here are the coefficients describing the second two port. And then here is what is at the input of the second two port. So I've just rewritten the equations appropriately. What I've written here is the third order intercept point now for this cascade of the two blocks in terms of the coefficients A for each of the two ports. It's a rather complicated expression. There's a factor of 2 over the square root of 3 out front. We take the square root of the magnitude of this rather complex ratio of expressions. I'm not going to derive that here, and it's not derived in the book. It's a relatively complicated derivation, but the result is clear enough. So here you have it. This is the third order intercept for a cascade of two ports, which can be described using a third order memoryless polynomial response model. Now, a more convenient way to do this is as follows. And what I've shown here is an approximation which is known to apply. Again, I'm not going to derive it. I'm simply going to write it down. But it turns out that 1 over the square of the third order intercept point is equal to 1 over the square of the third order intercept point for the first stage plus 1 over the square of the third order intercept point for the second stage, but in this case we multiply by the linear gain of the first stage. So the structure of this expression is as follows. We see that we have this kind of reciprocal relationship, except the second stage that we've now taken into account, we multiply by the linear gain of the first stage. And in fact, this expression, again, I'll show this without proof or derivation. I'll simply tell you what it is. It turns out that for any number of stages, we can continue this trend. So if we have, for example, 3 stages, here's what we get. We get that the 1 over the overall third order intercept point squared is approximately equal to the sum of terms here, where the first term is just like this first term here, and the second term is just like this second term here, and now we add a third term. And it may not surprise you to find out that is related to the reciprocal of the square of the third order intercept point for the third stage, and then in the numerator here we scale it by the squares of the linear gains for the first two stages. And we just continue that trend for as many stages as necessary. So here's that expression once again. I can write it in terms of power, right? Because these parameters are in terms of voltage or current, either one, depending on what I have in that particular problem. But as I've noted before, it's frequently more common and convenient to express things in terms of power. So if we can agree on the impedances, we can write this down in power units. The square of a voltage or current type quantity becomes a power. So I'll just rewrite that as shown here. And this expression I'll write as shown here. And similarly, I can convert this to a power. This is just linear gain in power units. Here's the third term converted to power, and then this numerator becomes the product of gains, and we continue that trend. So in power units, it's a little bit more clear how this equation unfolds with increasing numbers of stages. Here I've rewritten the expression for third order intercept point. Turns out the exact same idea applies to second order intercept point. And here's the new expression. You'll see it is exactly the same form as the expression for the third order intercept point. Very convenient thing to know. One thing you should note is that when all the gains are equal to unity, by that I mean when G1 equals G2 equals G3, etc., are all equal to 1, the cascade input intercept point cannot be better than the worst stage intercept point. So for example, in this expression, if all the gains are 1, then this is 1, and this product is 1. And I'm adding the reciprocal of these things together, and that gives me the result. So we see that we're limited by the input intercept point of the worst stage. Now this should remind you of something. This is exactly the way resistances work, right? If I have parallel resistances, there's one resistance, there's a second resistance, you know that the combined resistance here can't be greater than the lower resistance. You see here that when the gains are all equal to unity, we have the exact same kind of relationship. So I'm not implying that there's any special underlying relationship between intercept points and resistances, except in this mathematical sense, and that mathematical analogy is useful to see. We see that when the gains are all equal, the input intercept point of the cascade can't be any better than the input intercept point of the worst stage in the cascade. A very useful idea. You should also note that increasing stage gain tends to degrade a cascade intercept point. You can see that because, for example, if now I go from 1 for these gains to some greater number, that is going to degrade the overall input intercept point. Furthermore, we see that in practice the cascade intercept point tends to be dominated by the final stage, by the last stage, because that's subject to the complete cascade gain minus the gain of that last stage. So for example, here again, we see that each subsequent stage, the intercept point is degraded by the gain of the cascade of all the stages that precede that stage. So that tends to make the last stage in a cascade more important than the other stages when the gains are not all equal. Okay, so an example to show how this works. In this example, a system consists of two perfectly matched amplifiers, and they're shown here. The gain and the output third order intercept point of each of the amplifiers here is specified. The gain is said to be 15 dB in each case. Output third order intercept point is 15 dBm and 20 dBm here. And the question is, what is the input IP3 of this entire system? And then what is the output IP3 of this entire system? Well, again, using this idea of how to compute intercept points, I can do this if I convert the output intercept points to input intercept points. Those are different by the gain, right? So the input intercept point here is 15 dB less than the output intercept point because that's the linear gain. And similarly here, 20 dB becomes 5 dBm. So I have everything I need to evaluate this equation. It's simply a matter of converting from dBs to linear units and doing the computation. When the smoke clears, we find that the input intercept point, third order, is minus 10.4 dBm, as I've written here. And then the cascade output third order intercept point is simply that greater by the linear gain. And the linear gain of this cascade is 30 dB. That's simply 15 dB plus 15 dB. So if I add 30 dB to the input third order intercept point, I get an output third order intercept point of plus 19.6 dBm. Now we'd like to do a similar thing for noise temperature and subsequently noise figure. So here's a cascade of two ports. They're each described in terms of a gain and an equivalent noise temperature. And I apply a power spectral density to the input. This is something that would have units of watts per hertz. And I get a power spectral density out of the first two-port, and then subsequently a power spectral density out of the second two-port. And I would like to know what these things are, and then I would like to know how to compute the overall equivalent noise temperature. So this is actually pretty straightforward. You can write an expression for this quantity, the power spectral density out of the first two-port. It's simply the input power spectral density times the gain of the first two-port plus the input referred equivalent noise temperature of the first two-port, again times the gain of the first two-port, because this is input referred. So we can extract common factors here, and we get K times the sum of those two noise temperatures times gain of the first two-port. I can then write an expression for the power spectral density out of the second two-port. It is simply the power spectral density that is delivered to the first two-port, and here we're evidently assuming everything is matched, impedance matched, so we should remember that that's being assumed here. The input power spectral density is multiplied by the gain of the second two-port, and then we add the additional noise that second two-port delivers. That's K times the input referred equivalent noise temperature of the second two-port times the gain of the second two-port. So now making the appropriate substitutions and factoring away here, I get a K out front, I get the cascade gain, G1 times G2, and inside here I get Tn plus the input referred equivalent noise temperature of the first two-port, and then the input referred equivalent noise temperature of the second two-port, but now divided by the gain of that first stage. Now take a look here. In this first expression, this quantity here maps to this whole quantity here in the second expression. So going from one two-port to a cascade of two two-ports, we see the only thing that's really changed here is this part of this factor. So I can conclude from that the input referred equivalent noise temperature of the cascade is simply the input referred noise temperature of the first stage times the input referred noise temperature of the second stage divided by the gain of the first stage. Now frequently I want to know the noise figure, but that's simple enough to figure out. Noise figure is simply 1 plus equivalent noise temperature divided by the reference temperature. So we're going to have to agree on what reference temperature is. And remember, I say noise figure here. Some people would say noise factor. So I make that substitution that I just came up with for the equivalent noise temperature of a cascade. I work through the equation, and what I find is that I get the noise figure of the first stage plus the noise figure of the second stage minus 1 divided by the gain of the first stage. So this is what I get for two stages. So now I know how to compute the noise figure of a two-stage cascade given the parameters for the two stages. I can extend this idea to any number of stages, quite simple exercise to do. What you find is that the cascade noise figure is given by the noise figure of the first stage, and then this expression for the second stage, and then this term accounts for the third stage. So for each subsequent stage we see a fraction, which the numerator is noise figure minus 1, and the denominator it's gain of the cascade that precedes that stage. So for the second stage it's just G1, for the third stage it's G1 times G2, and so on. Let's do an example to reinforce this idea. In this example we have an actual device here. The Mini Circuits GALI 74 mimic amplifier. This is a real part. It's based on bipolar transistor technology. This device has a gain of 25 dB and a noise figure of 2.7 dB at the frequency of interest, and it's shown here in this diagram. We put it in cascade with this other mini circuits device. It's a GVA 81, has a gain of 10.5 dB and a noise figure of 7.4 dB at the frequency of interest. Port impedances are 50 ohms throughout, which is telling us that everything is matched. And now we'd like to know what the combined noise figure is. So this is pretty straightforward. We have all the parameters we need to do the cascade calculation. The details are shown up here. What you get is that the noise figure becomes 2.73 dB. Now it's interesting to compare that 2.73 dB to the stage noise figures. The first stage was 2.7 dB. The second stage was 7.4 dB. We see that the cascade noise figure is only slightly worse than the noise figure of the first stage. And the reason is because the gain of that first stage is very large. And so that very large gain kind of locks in the signal to noise ratio at the input of that first stage. Here's another example problem, something that's not uncommon to see in practical engineering problems. Here we have a long coaxial cable inserted between the two amplifiers. So same problem as before. We have the same two amplifiers, the GALI 74 and the GVA 81 over here. But now we've inserted coax. The coax has a gain, and that is in this case a loss, but a gain of minus 4.1 dB. If we assume the physical temperature of the cable is equal to the reference temperature, if we use 290 K, then the noise figure of the cable is going to be simply 1 over the gain, or that is the loss. So we get the noise figure is simply 4.1 dB here. And now we have everything that we need to work the cascade equation, right? We can compute the cascade noise figure using the expression I just derived. And here's what we get. We get the noise figure is 2.8 dB. So this is pretty remarkable. We started off with a noise figure of 2.7 dB in that first stage. We have a ton of loss here, and then some gain here, but with a much poorer noise figure. And yet the cascade gain is only slightly worse than the noise figure of the first stage. And that's usually what we want. We usually want to try to lock in the noise figure early on so that subsequent losses in the system do not significantly degrade that noise figure. So this is a very typical kind of situation to be in. So this whole thing kind of raises the question of the significance of stage order. Now what do I mean by that? This is best shown by example. In this example, which is straight from the book, which I'm going to go through here, we have a base station. This base station is for an LMR application. LMR here means land mobile radio. So this would be something, for example, that police or fire or other public safety organizations would use. But we have an LMR base station. A receive path consists of a mast-mounted antenna separated by a long cable having 10 dB loss at the frequency of interest. And the receiver in this system consists of two parts, has a front end which includes the antenna, cable, and two amplifiers, and a back end consisting of the rest of the receiver. Now somebody's already gone ahead and done the analysis, and we know that the front end is specified to have a gain of 35 dB. And to accomplish this, two amplifiers are provided. Here's the first amplifier, has a gain of 15 dB, has an output third order intercept point of 5 dBm, has a noise figure of 4 dB. Amplifier number 2 has a gain of 30 dB, an output third order intercept point of plus 10 dBm, and noise figure of 8 dB. And the cable has a loss of 10 dB. So if we assume the cable's at the physical temperature, then the noise figure is 10 dB. And we're also, of course, assuming that the reference temperature is set equal to the physical temperature. And as you know, that introduces a small amount of error if this is not exactly true, but usually it's pretty small. Now we have some requirements. The noise figure of the front end is required to be 7 dB or better, and we're asked to design the front end. Now design here means simply choosing the right components in the right order. So one possibility is I can just connect these together as shown here. Another possibility is I could have the cable first and then amplifier 1 and amplifier 2, or I could have the cable first and then amplifier 2 or amplifier 1. All the possible ways I can combine 3 stages are a possibility here. The gain must be 35 dB. Well, that's going to happen automatically here because 15 minus 10 plus 30 is 35 dB. So this is going to be achieved automatically. The output third order intercept point is not specified. But the noise figure has to be less than 7 dB. So the problem here is find the arrangement of these 3 stages that gives me a noise figure less than 7 dB, and then perhaps I want to consider also the output third order intercept point, even though that hasn't been specified. Well, I can start with the cable. If I put the cable first, I'm obviously not going to meet the noise figure requirement because the noise figure of the cable is 10 dB and the spec is 7 dB for the system. So if I put the cable first, that's an automatic fail. So that's obviously not a solution. Another approach would be to put the second amplifier first. If I do that, I find the noise figure spec can't possibly be achieved because I have 8 dB here and I need to get 7 dB. So any solution that works requires putting the first amplifier first. So now I've got 2 choices. Either I can have the cable first or I can have amplifier 2 first. So these are the 2 possible systems that I should evaluate. So here's a stage cascade analysis. This is the one where we have an amplifier, cable, and then amplifier. So this is the one where the cable goes in the middle. And this is a very typical way to display the results. So here I'm showing the gain, input third order intercept point, and noise figure for each stage. I'm also indicating here the cascade results. So this is the cascade gain, third order intercept, and noise figure. So here the cascade results are the same as the stage results because the cascade consists of only one stage. Here the cascade results are for the first and second stage, and then here the cascade results are for the first, second, and third stages. So this is the overall gain, this is the overall input third order intercept point, and this is the overall noise figure. And then just for reference, I'm also showing here the equivalent noise temperature. So that's the stage equivalent noise temperature, and this is the cascade equivalent noise temperature. So these 4 numbers here are describing what I've got for the system for this particular cascade. And then the other option looks like this: amplifier 1, then amplifier 2, and the cable. Again, the only difference between these two is what order cable and amplifier 2 appear in. So what is interesting here to look at is the cascade results for the first 2 stages and then for all 3 stages. And then what I really want to compare is these things, the cascade results for the 2 systems. And what I see, of course, is the gain is the same for both. That's because the stage order has no effect on the gain. However, I see for the input third order intercept point, there is a difference. In fact, there's a 10 dB difference. This one's much better for input third order intercept point. The third order intercept point is much higher. However, for noise figure, I see that this one has much better noise figure. So we see that stage order has had a significant effect in the results here. So summarizing, this approach has much better noise figure but relatively poor linearity. This one barely meets the spec because this had to be less than 7 dB, but it has better linearity. So which one do you choose? Well, if you're trying to minimize noise figure, that is trying to get the best possible sensitivity, well, you might choose this one. However, if you're concerned about linearity, perhaps you're in a high signal environment or high interference environment, then you might choose this one because it has a higher third order intercept point and the noise figure meets the specification. So you really need to know a little bit more about the application to make a decision here, but this is a classic trade-off. So now let me summarize what we've talked about in this lecture. In practice, the choice between the 2 options I just showed you would be settled by other factors. Could be that neither option is acceptable. and that linearity needs to be increased. That's also a possibility. But using stage cascade analysis, you can now quantify the trade-off that you have to deal with. This form of analysis is very common in the design of receivers. It's commonly referred to as stage cascade analysis, sometimes referred to as gain, noise figure, and intercept point analysis, identifying specifically what we're looking for in this analysis. And we see that the typical trade-off emerges between sensitivity and linearity. I call it typical because I referred to it probably in the first lecture in this course. The fact that things we do to improve sensitivity tend to degrade linearity and vice versa. And it's very difficult to have both be very good. It's common that improvements to one degrade the other. This completes this lecture on stage cascade analysis.